That's another question. I'm saying yes because you said one sheet. You didn't say one side.
All right. So, last day of class before exam number 1. Exciting. Just as a reminder for all you people who are going to be taking it on campus, it will be tonight starting at 6 o'clock in ERC 214. I'll shoot to try to be here at about 10 minutes to 6, so if you want to perhaps even get started a couple minutes early, we can do that. I think that there will be a couple of online students who will be joining us, so feel free to bring pop or snacks or whatever you might need to get you through. In terms of today's class, we've got one last topic to cover for Thevenin equivalence, which is what to do when you have a mixture of independent and dependent sources. So we'll take a look at least one or two examples of that, and then once we've done that, we'll transition into number 1. That'll be the end of the material for chapter 5, anyways, and then we'll transition into the material or just a review session. So talk about what I know is on the exam, what kinds of things that you should be expecting, and then give you an opportunity to just ask any questions, have me do any example problems or whatever. So quiz 3 is going to come back as it's making its way back. I'll take a quick look at it. Everybody got the same kind of quiz, even though the the numbers were slightly different for each one of the problems. So we'll look through the one that the on-campus students did, so that you can get an idea of what the proper solution should look like. And for the online students, you'll just plug in your appropriate numbers and take care of it that way. So I did actually make it through all of the 3 things on my priority list yesterday, although the homework assignment didn't get posted until like 10 o'clock. But it did go up, so I got it done. I'm expecting a due date of, we've covered all of the material just about, so we could get it done kind of whenever, but I may push it off to as far as like Wednesday, just so that you have enough time to work on it. I'm getting some dirty looks here. Yeah. All right, so let's take a look at the quiz real quick, and then we'll get back into Thevenin analysis, try to get all this stuff done. So, all right, so the quiz. Everybody got, like I said, the same basic form of the circuit, which had dependent source up here at the top, dependent current source, and resistor here, and voltage source here, another voltage source down here, a current or a resistor here, and a resistor here. So it worked out, the parameters given to the on-campus students, the source was a 6-volt source. This one was a 10-volt source. The current source gave out 2Ix, where Ix is the current running through this 10K resistor here. This is a 5K resistor, and what you were asked to solve for was the current I0 flowing in the indicated direction through the 5K resistor. The last one over here is a 3K resistor. So that's the setup for the circuit itself. And you were asked to use mesh analysis to solve for it. So what we need to start thinking about is, where do these mesh currents actually go? And a couple of them are fairly straightforward, I think. We'll call I1 going up there. And people ordered the meshes in different ways, and it doesn't really matter. I managed to follow what you all did. But I'm going to put I2 down here and I3 running over here. I saw a couple of people trying to do super mesh things with this, And there's no need to try to do a super mesh with this problem because the only source that's shared between two loops is a voltage source, and that's not a problem. We don't have to worry about that. I think in theory, as long as you define the meshes correctly, you should still be able to define a loop that went down and around. That shouldn't be a problem, I think. But you can do this as a fairly straightforward, just 3-loop problem instead. So what we can say right off the bat is constrained by the current source, I1 simply equals 2 times Ix. And then we need to write our controlling equation for what Ix actually is, and that is I2 minus I3. So those are the two kind of easy ones to deal with, and now we need to deal with the two other currents that we have introduced here. So the first one going around loop 2, we run into the negative terminal of the 6-volt source, then we've got 5K times I2 minus I1, and we've got then 10K I2 minus I3 equals 0. And you can simplify that one. There's actually a couple of different ways that you can do this. It works out in this particular problem numerically that if you plug in the information that we know about what Ix is, and we make this, that I1 is 2I2 minus 2I3, and you plug this in here, all of the I3 terms disappear from this equation, and you can solve directly for I2. It just happens to work out that way. But in terms of a more general approach, we can just solve it, and just simplify all the terms so that we see a negative 5K I1, we see a positive 15K I2, and a negative 10K I3 equals 6. So this is one of our equations we'll use to solve here. Third, around the loop labeled I3, we have the 10K resistor times I3 minus I2. We've got the 10-volt source, and we've got the 3K resistor, which just has I3 running through it, and that equals 0. So solve that one. Just to kind of make life easy, let's say that there's 0K I1 minus 10K I2 plus 13K I3 equals negative 10. So that's our second equation. And the way that is, I think, the most general way to solve this is to take this information, plug it into here, and so you get I1 equals 2I2 minus 2I3. And then rearrange the terms so that it's just in a nice general format of I1 minus 2I2 plus 2I3 equals 0, and use that as your third equation. So if you put those three equations into an equation solver or a matrix or whatever, what you will get out of it is that I1 equals 2.092 milliamps or thereabouts. I2 equals 1.2 milliamps. And I3 is about 154 milliamps. So that's what you get when you solve for your loop currents. Again, that's not quite all of the problem, though. The last thing that we need to do is solve for I0. In this case, I0 is given as, it's going the same direction as I1, and the opposite direction as I2. So I1 minus I2, given my loop labelings, will give us I0. That's 2.092 minus 1.2, which gives us 0.892 milliamps. So that's, that's the I think the most straightforward way to do it. You can also, you should get the same answer. Again, what I did was try to set it up so that it was the most straightforward way to stick it into an equation solver or something. So that's, we've got 3 equations in terms of, and with 3 unknowns, the I1s, I1, I2, I3 in this equation, this one, and this one. You can plug that in and get all of these numbers. Or again, the math on this particular version of the problem works out such that if you plug in what you know about what Ix is, plug that into this first equation, you can solve directly for I2. The I3 terms essentially cancel each other out. You can solve directly for I2 and then plug that into your equation that you wrote for I3, solve for I3, go back and solve for I1 with what you found out that way. But any questions on how we did that one? Okay, so I don't think that anything on the exam would be even this hard, at least in terms of the mesh and node analysis problems. There are a couple. I know there's at least one problem that asks you to do an analysis with a dependent source, but I think there's just the one, so should be pretty straightforward. So, okay, so let's. If you have any questions on the way that I graded your quiz or anything, please let me know, and we'll take a look at that. Just in the way of a quick review of the things that we talked about yesterday. The key thing that we took a look at was the dependent source equivalence, how to deal with finding the Thevenin equivalent for a circuit that contained only dependent sources. And what the extent of that equivalent was a Thevenin equivalent resistance. That was all. But we can't just short out dependent voltage sources or open up dependent current sources. The only way to solve for this is to attach a test source of some kind, either a 1 amp or 1 milliamp current source or a 1 volt voltage source, and then solve for the other parameter. What is the current that's running around? What is the voltage across the source? And once you have those two things, then the ratio between them is going to give you your Thevenin equivalent resistance. So that's that's going to be our problem-solving scheme. I did put one simple one on the homework for that for you to take a look at. So that's not I don't know that that's a particularly interesting circuit to look at. It is just for the sake of completeness so that you understand how you deal with that kind of circuit. And then we did a whole bunch of examples of dealing with independent sources, and I think that's fairly straightforward. So that's the last thing that we're that's what we covered yesterday. The last thing to cover in terms of Thevenin and Norton equivalents are what happens when you have mixed sources. Just to go back again one last time on this, I asked Dr. Mbardar, who's taught circuits just about forever, and he taught me circuits when I learned it, and has won a couple of different distinguished teaching awards here at the university, and won the best instructor award so many times as nominated by the students that he actually took his name out of the running. He said, "Stop voting for me." But either way, I asked him, I said, is there any rule of thumb, anything that I can tell the students in terms of which one of these do you use? And he said, no. There's no particular, nothing that I can tell you that says if you always hook up a 1 volt source if there's a dependent voltage source or anything like that. I can't tell you anything like that. The only thing that I can particularly tell you is, if you like nodal analysis more than mesh analysis, hey, maybe you should add a voltage source, because voltage sources in nodal analysis are pretty nice, at least when you're hooking it up. It depends on where you're hooking it up though too, right? If you're trying to hook it up where that voltage source would cause a supernode, well, maybe you want to take a look at a current source instead. there's no real good rule of thumb. So as much as anything, it's a good reason not to just do the problems in the first place. But anyways, so when we have a mixture of independent and dependent sources, what we have to do, unfortunately, is that we can't just short out the sources. Or we can't zero out the sources. The only thing that we have as an option is to solve for both the open circuit voltage and the short circuit current. The ratio between those two is going to give us the Thevenin resistance. And then since you have the open circuit voltage and the short circuit current, you can obviously create either Norton or a Thevenin equivalent, depending on what you want to try to do. One of the key things to remember, though, as you're breaking the circuit and finding, especially if you're going to do multiple iterations of a Thevenin equivalent, is that you have to make sure that you never eliminate the controlling parameter for a dependent source and take that away from the source or from the circuit as you're working on it. And that may seem somewhat obvious, but you still have to be careful about it. So an example, So let's look at least one example here. And I've got 3 total problems to look at for this, and we'll do at least 2 of them. So the first one has a dependent voltage source on the far left-hand side here with a value of 2,000 times some current Ix. This is a 1K resistor, this is a 2K resistor, here's a 12 volt source. This is a 2K resistor. Here is the controlling parameter Ix. Here's a 1K resistor. Here's another 1K resistor. And the thing that we're interested in, V0, is the voltage across that far right 1K resistor. So no matter what we want to do, in this case, if this was a circuit and this happened to be an independent voltage source, we might want to go through and try to do maybe 2 sequential Thevenin equivalents, break the circuit here, find out what the open circuit voltage is across the 2K resistor, and then do it again as we go across. But we can't do that because in this case, we won't know what the voltage being created by this is unless we include the controlling parameter Ix. So the very farthest to the left or to the right that we can break this circuit would be right here. That's where the book does it. You could just as easily break it to the right of the 1K resistor, and all it's going to do is save you a step when you're doing the Thevenin equivalent resistance stuff. But either way, we'll break it here to be consistent if you wanted to follow along in the textbook at all. But so that's where we're going to break the circuit, and we need to start doing a certain amount of analysis to figure out what's going on. So here's the circuit once we've broken it. $2K resistor, 12, 2K, 1K, 2K Ix. And that's still where Ix is flowing. And so we need to find our open circuit voltage will be the voltage across that 12K resistor. Now, the way that I've got the analysis done here in my notes, and I'm going to follow along with that to make sure that I kind of stick around with the right answer, is to introduce 2 nodes, V1 and V2, and that's going to be a supernode, unfortunately. But that means that we only have to write one equation, more or less. But so V1 minus V2 equals 12. That's our supernode equation, the one that relates the 2 nodes. And then we write the KCL equation at the supernode. We've got V1 minus a negative 2kIx or plus 2kIx over 1k. V1 over 2K and V2 over 2K equals 0. Last thing that we need to do is quantify what Ix is in terms of one of our other circuit parameters. Easiest way to say that is, well, that's V2 over 2000. Because the voltage across the 2K resistor is we've called V2, and dividing it by the resistance will get us Ix. So Ix equals V2 divided by 2K. And furthermore, what's going to it's interesting to make sure that we realize is that the open circuit voltage is the same as our node voltage V2. It's the same thing. So what in this case would be most beneficial is that if we can solve for V2 in this single node equation that we have, that would be the easiest thing to do, give us the most useful answer. So let's rewrite this equation as V1 equals V2 plus 12. So that will allow us to rewrite this this node equation solely in terms of V2, get rid of all of the Ix's and stuff like that. So here, equation should still be visible. V1 is V2 plus 12, so we have V2 plus 12 plus 2K times Ix. Well, Ix is V2 over 2K, so the 2Ks cancel out, and you just get V2. And that's over 1K plus V2 plus 12 over 2K plus V2 over 2K equals 0. Let's multiply both sides by 2K to get rid of everything in the denominator, and so we get 2V2 plus 12 times, I guess that's, well, the 1,000 goes away, so it's 24 plus 2V2 plus V2 plus 12 plus V2 equals 0. So get the constants over on one side, that's negative 36. And we've got 2, 4, 5, 6 V2s. So 6 V2 equals negative 36. Divide both sides by 6, and we get V2, which is the same as our open circuit voltage, is negative 6 volts. A lot of work there. The next step, this is where things are going to get a little weird, okay? And this is going to happen frequently as you're doing this kind of analysis with these dependent sources. And this is going to, you have to be ready for this and realize that kind of perhaps even what your intuition is about what's going to happen to this circuit is really indeed what happens, okay? So look back for a minute at, this was our circuit that we created when we broke it to the right of that 1K resistor. So this is where we're going to draw in our short circuit, is between these two terminals just to the right of that 2K resistor. So let's draw what that circuit looks like. So we've got the dependent source hanging out over here, minus plus, the 1K resistor, we've got the 2K resistor, we've got the voltage source, we've got the 2K resistor, and we've got these terminals hanging off, and then we're going to short circuit what's going on over here. And what we need to solve for is, this is our short circuit current. Here's our 2K Ix voltage source, our 1K resistor, our 2K resistor, and our 2K resistor. So this is the circuit that we need to analyze now. Now, one of the things that we saw even back in one of the very first homework assignments is that when you have a short circuit in parallel with a resistor, that resistor in effect goes away. because the current will always go through here, and that resistor, for all intents and purposes, doesn't exist in the circuit. So essentially, we can take that out, or at least no current runs through it, and so there's no point in. I mean, it's shorted out. It's gone. But that has an important consequence. If that 2K resistor is shorted out, then what is the current that's running through IX? 0. If IX is 0, what is 2,000 times IX? Well, it's still 0. So this voltage source is also shorted out. So the circuit that we're actually going to be working with, this voltage source gets shorted out. We've still got the 1K resistor. We've got the 2K resistor. We've got our 12 volt source. And that's it. That's all that's left in our circuit. 1K resistor and the 2K resistor and the 12 volt source. That's all that's left. And this is a pretty easy circuit to analyze. I think we can do that pretty reasonably. My notes are very strange in this. So to find out what that current is, let's combine the 1 and the 2K resistors in parallel. So 1 over 1 plus 1 over 2. Flip that. We get, that is a lovely 2/3 K resistor and a 12 volt source. The important thing here will be to remember that in actuality, the current is going to be flowing the opposite direction that we've defined the short circuit current is running because of the polarity of the voltage source. But the magnitude is going to be very straightforward, that we've got 12 volts divided by 2/3 of a kiloohm, which is, well, I'm just going to use my notes, it's 18 milliamps. So the magnitude of the current is 18 milliamps, but that's going around the opposite way as our short circuit current actually is going. So I short circuit equals negative 18 milliamps. So our open circuit voltage was negative 6 volts. Our short circuit current was negative 18 milliamps. So our Thevenin resistance equals the voltage, negative 6, divided by the current. That's right, negative 18 milliamps. So 6 divided by 18e, negative 3, gives us 333 ohms, or 1/3 of a kiloohm. Now, here's one thing that you can use as a bit of a sanity check. If you ended up with a negative open circuit voltage, hopefully you end up with a negative short circuit current, because I have no idea what a negative resistance is supposed to mean. As far as I know, that has no physical meaning of any kind. It's a meaningless concept. That should be something you can use to check your work and make sure you ended up with something that has some meaning. Because if you end up with a negative resistance, I really don't know what that's supposed to mean. But that's our circuit. That's what's happening with this. So we've got our open circuit voltage, we've got our short circuit current, we've got our Thevenin resistance, and we can solve for whatever it is that we want to solve for. In the original version of the circuit, what we had that we wanted to solve for, so here's our Thevenin resistance, 1/3 of a kiloohm. We've got the 6 volts. One thing that we left in the original circuit was a 1 kiloohm resistor, and the advantage of leaving that off is that we got this behavior with the short circuit current, that it got rid of the IX and the voltage source and stuff and simplified our analysis. So what we're left with is the 1/3 K resistor. This is our Thevenin equivalent over here. And then we've got the two 1K resistors that were left. I think that's right, yeah. So we can do a little bit of a voltage divider here and say that the voltage V0, defined as it is, we'll have to make sure that this is -6 volts to get the right numeric answer if we, as we're going a KVL around the loop. So V0 is some fraction of the -6 volts, which is 1 over 1 plus 1 plus 1/3. And that happens to equal, and if you have a pretty print calculator, it's -18/7 in fractions, or decimal, that's about -2.57. So let's do one more of these at least, and if you want to, we can come back and do more. But this is another fairly straightforward problem. Volts here. This is a 4 kilo ohm resistor, and the voltage Vx across that is the controlling parameter here for a dependent voltage source with the value Vx over 2. And this is a 4K resistor. And what we want to analyze is what is the voltage across this 6 kilo ohm resistor here. And we want to find V0 when we're done. So that's what we're trying to do. In this case, there's no functional difference between where we would want to break the circuit and where we have to break the circuit. We just rip out our load, and that's what's left. And so the open circuit voltage will be the voltage across the 4K resistor, and essentially plus the voltage that's across this dependent source, but the polarity is different, is backwards, so you'll end up subtracting that value, just because think about it in terms of the KVL around the loop. We run into the positive terminal of that and the negative terminal of that, so adding these two voltages together they've got opposite signs. So here's our circuit that we need to find. We're actually going to analyze the 4K resistor, the dependent source, find the open circuit voltage, 4K, Vx, 4K, 12 volts. And this time it works out that we can just write a single KVL equation, characterize what the current is that's rolling around in the circuit, to find out what the voltage is across each one of these 4K resistors, because the voltage across this 4K resistor directly contributes to our answer. The voltage across this 4K resistor tells us what Vx is, which is what's going on over in this voltage source. So let's write the ones KVL equation. We'll walk around in a clockwise fashion. Get -12 volts plus 4K times whatever the current is, I, plus another 4K times I, minus Vx over 2 equals 0. We need to write our controlling equation, which is Vx equals 4K times I. So we can stick that up into here. And so that's going to be 4K times I plus 4K times I minus 4 over 2 is 2, or 2K times I, and that equals 12. So that's 8 minus 2 is 6. 6K times I equals 12. So I equals 2 milliamps. So the open circuit voltage is going to be the voltage across the 4K resistor, which is 4K times 2 milliamps, minus Vx over 2, Vx, so that's 4K times 2 milliamps over 2. That's 8. That's 8 over 2, so 8 minus 4 is just 4 volts. So there's our open circuit voltage. This time, when we do the short circuit current, things don't work out quite so, I guess handily, in that things are getting canceled out left and right. I think the easiest way to do this is as a little bit of a mesh analysis problem. And if you do it and you just define the currents I1 and I2, in this case, the short circuit current we're solving for is equal to I2. So whatever our answer is for that will get us through that. Our controlling equation is that Vx equals 4K times I1. So write our two mesh equations. We've got negative 12 plus 4K times I1 plus 4K I1 minus I2 minus Vx over 2 equals 0. So 4K, sticking the information in for Vx, that's 4K over I1, which leaves us with 2K over I1. So we got 4K I1 plus 4K I1 minus 4K I2 minus 2K I1 equals 12. So that's 6K I1 minus 4K I2 equals 12. Going around the second loop, we've got Vx over 2. Just for our reference, Vx over 2 is going to be 2K I1, so we can stick that back in friendly places. So let's just stick that in, say we got 2K I1 plus 4K times I2 minus I1 equals 0. Or, see, that's 2K I1 plus 4K I2 minus 4K I1 equals 0. So we get negative 2K I1 plus 4K I2 equals 0. So these are our two mesh equations. Solve those simultaneously, see what we get. 6,000, negative 4,000, 12, negative 2,000, 4,000, 0, solve. And we get that I1 equals 3 milliamps, and I2 equals our short circuit current is 1.5 milliamps. So we've got our short circuit current. We previously solved for an open circuit voltage of 4 volts. So our Thevenin resistance is the ratio of the 4 volts to the 1.5 milliamps. 4 divided by the pretty answer to that is 8/3 of a kilo ohm. And that's, numerically, that's 2,666.67 repeating, no, 0.6 repeating. So we can build our circuits and then do any analysis on it that we want to do. What we figured is that we had an open circuit voltage of 4 volts. We had a Thevenin equivalent resistance of 8/3 of a kilo ohm. And we can hook our load back up, which was the 6 kilo ohm resistor, and do a simple and what we wanted to find out in the first place was the voltage across the 6K resistor. Just do a simple voltage divider. So V0 equals 4 times 6 over 6 plus 8/3. And according to my notes, there's no answer. It just stops there, apparently. Cool. All right, so 6 divided by 6 plus 8 divided by 3 times 4. According to this, is something like 2.6769. Let's see if that's got a nice, which is apparently the beautiful value of 36/13. So, all right, to make sure that there's enough time for questions and stuff, I'm going to wrap this up, and but I'm more than happy going into Monday to answer some more questions if you are not feeling comfortable with the dependent source analysis. But just to keep things kind of moving along and whatnot. So, all right, so summing up the entire Thevenin equivalent thing up on those PowerPoint slides. The process of doing a Thevenin equivalent will be to, number one, remove the load, whatever that happens to be, and find the voltage across the open circuit terminals. And you can use any analysis tool that you want to. You can, if you want to, you can do this repeated times, breaking it in smaller and smaller places. And so then in that way you never have anything more complicated to do than a voltage divider or something like that. Or you can break it immediately just to the right, just to the left of the load, and do whatever it is that's, use any analysis tool, mesh analysis, loop analysis, voltage or nodal analysis, whatever. You can use superposition too if you want to. Hey, whatever is comfortable to you. Then determining the Thevenin resistance is step 2. If you have nothing but independent sources, the beautiful thing is that you just zero them out appropriately, and that means that all of the current sources are open circuited, and you just rip them out, leave a gaping hole in the circuit. The voltage sources are set to 0 volts, which is a short circuit, and they're replaced by just a line for the conductor itself. If you have only dependent sources, then you kind of actually skip the first step because we're not going to actually solve for the open circuit voltage. We're just going to attach a test source. And like we mentioned, whether you pick the voltage source or the current source is up to you, whichever you kind of like or whichever makes the analysis of the circuit look easiest. Once you find the other parameters, so if you hook up a voltage source, solve for the current. If you hook up a current source, solve for the voltage. The ratio between those two things gives us the Thevenin resistance. If we have a mixed number of sources, then we need to find the open circuit voltage as well as the short circuit current. And you have to make sure that whenever you break the circuit, you never break it such that the controlling parameter for your dependent source is eliminated from the circuit. You may find that as you solve for the short circuit current, weird things may happen, like in our first example where the short circuit that we added to solve for short-circuited one of the resistors, which meant that no current was flowing through that resistor, and therefore the dependent source was also putting out 0 volts. That stuff happens quite a bit when you're doing that kind of analysis. And then once you're done with that, you have a Thevenin. You at least, depending on how you followed this, you may have a Thevenin open circuit voltage. You may have a short circuit current, and you have a Thevenin resistance. You can create a Norton equivalent, a Thevenin equivalent, solve for whatever you want to solve for using whichever analysis method is appropriate. More than likely, what you're down to at this point is probably just a current divider or a voltage divider. So life is pretty straightforward there. Why would you want to do this? At this point, the primary thing that a Thevenin equivalent does is gives us understanding as to how a given circuit's element contributes to the overall behavior of the circuit. Because if you start mucking around with anything else in the circuits, change one of the resistors on way far away from the load, now we don't have any clue as to what the behavior, because now our Thevenin equivalence has changed considerably. But at least this gives you some insight into the way that why a circuit behaves the way that it does, or at least the value of a certain parameter. The other thing that you can do is if you want, and the chapter gets into this in a little bit more detail, but another thing that you can do is maximum power transfer. So if you want to know, if I want the greatest power to be delivered to my load, given the rest of the circuit, how can I do that? And the way to do that is to always make your load resistor equivalent to the Thevenin equivalent resistance. The reason being that in that case, the same amount of current or the same amount of voltage would be across the Thevenin resistance and your load resistance, and that's the only way to balance those two, or to get the maximum amount of voltage, maximum amount of current across that, and get the most amount of power delivered to that particular resistor. And again, the book talks about that a little bit more. So that's another reason. If you want to figure out what a resistor should be to get the greatest power transfer to it, Thevenin equivalence will give you that. Another thing that we will see, that even if you don't like the rest of the Thevenin analysis, the Thevenin resistance shows up when we start doing transient circuits, when we're looking at inductors and capacitors and the circuits, when we start flipping switches and seeing how these elements behave. The Thevenin resistance gives us a clue as to how to solve for that and whatnot. So there's a lot of reasons to still study Thevenin resistance or Thevenin equivalence, even though we have things like PSpice and calculators. So that's the summary. I'm not going to spend a lot of time with that. I just want to jump into the exam review so you can take a look at that as well. So the stuff that might be on the exam. This is, again, when I put these slides together, I look at all of the stuff that we've covered. And I have this kind of stuff in the back of my mind or whatever as I start to write the exam. And this is comprehensive. There's no way that I can squeeze everything that we've talked about onto a single exam. It's just, it's obviously too much. But these are the things that I think are important enough for you to make sure that you've studied and are ready to perform come the exam time. So like I said, you'll need to know how to do any of this stuff if you want to do well on the exam. From Chapter 1, there's not really anything in particular. I don't really care about whether or not you can integrate a little waveform of current to tell me what or of charge to tell me what the current is, or anything like that. The only thing that really might show up, and more than anything, is just, do you understand what the way that the passive sign convention works? So that when you're doing things like Thevenin equivalents and KVLs and whatnot, that you write them the appropriate way. Otherwise, the only other thing that's interesting in Chapter 1 is that power equals voltage times current. And that's about it. From Chapter 2, we get into Ohm's law. So know that V equals IR, and then be able to substitute that into the original power equation. So V squared over R and I squared R also give you power. You can try to remember, or if you've got limited space, don't bother with conductance, but it's really, it's just the reciprocal of your resistance. An infinite resistance is an open circuit, which means that there's no current running in that part of the circuit. A short circuit means there's no voltage. That doesn't mean there's no current, and there probably is current, but there's no voltage in that part of the circuit. KCL says that the sum of the currents entering and leaving a node is 0, or at least everything that's coming in goes out. The sum of everything going in equals the sum of everything leaving. And KVL says the sum of the voltages around a closed loop is 0. Those should be pretty comfortable by now. Getting into the latter part of Chapter 2, voltage division is pretty straightforward, so you should be able to easily perform voltage division now. I don't know that there's any problems that specifically ask you to do that, but voltage division is pretty straightforward in terms of, put the resistor on the top that you want to specifically solve for, put the sum of the resistances on the bottom as long as they're in series. And so the voltage across one of those resistors is a fraction in direct proportion to the size of the resistor itself. So the larger resistance, the more voltage across there is. Current division, you put the other resistor on the top of a pair of two resistors and the sum of the resistances on the bottom. Multiply that by the source current and you get the current that's running through that given resistor. And that indicates that current does take the path of least resistance. The larger a given resistance is, that's going to drive the denominator up while keeping the numerator small. And so you're going to get a greater or a smaller percentage or a smaller fraction of the current that runs through a larger resistor. Combining resistors in series, you just add them up. Combining them in parallel, you add them reciprocally, and then don't forget to hit the negative 1 power on your calculator to get the final parallel resistance. That's the first thing that I remember as being a specific problem on the exam, is that you are given a network of resistors to simplify down to a single equivalent resistance. Don't be scared by dependent sources. Be able to analyze them. There is a problem on the exam that asks you to, it's a fairly simple circuit, and I just want you to analyze it and tell me what the numeric value that's coming out of a dependent source is, given the other parameters in the circuit. Let's see. Chapter 3, the bulk of the exam comes from this chapter. So you need to be able to do both nodal and mesh analysis, and need to be able to handle all of the wrinkles that I could throw at you potentially, including dependent sources, supernodes, supermeshes. You need to be able to do those things, but bear in mind that my idea of what makes a good exam is to give you the core concepts and not to throw anything at you that's particularly strange. So if you shouldn't need to do a supernode on the exam, but you need to know how to deal with them. At least in terms of I know that there's a question that does ask you to do at least a little bit with a supernode, but you don't have to do the problem all the way to the logical conclusion. There are only two problems where I ask you to do the work all the way through, and it's your choice as to what analysis method you want to use to solve for that. You can do it as a Thevenin equivalent, you can do it as a nodal analysis or a mesh analysis or whatever. The other ones they give you the network and just say, write the equations around this loop. Write the equations for the supernode. Write the equations at this node. And then simplify it, and that's it. And so that's all you have to do for those particular questions. After that, I think there's 7 or 8 questions on the exam. Only 2 of them are full-blown circuit analysis. The other ones are things of a slightly smaller nature. So I did not put any specific problems about superposition or scaling. However, if you choose to, you can always use either of those analysis techniques on the final problems if that's what you want to do. If you want to, if that's your choice, I don't care. And there is one simple Thevenin equivalent circuit. It should not be overly complicated to do it. And all you have to do is find the open circuit voltage and Thevenin resistance. You don't have to actually go through the full solution of the problem. And what was the other? And it's only independent sources. That's the other thing that I wanted to mention. It's strictly independent sources for the Thevenin analysis. So that's it for what the material is actually going to be. As opposed to the scoop exam that I posted on Blackboard, I think yesterday sometime, this is 100% problem solving. There are no short answer questions on it. So do the work and that's it. The number of points on a question is focused mainly on the circuit analysis. So again, on like a 5-point question, 3 of the points will be for writing the correct equations, and only 2 points will be associated with algebra and getting the correct numeric answer. And that kind of thing will continue through. Again, mostly working partway through a problem, and a solution would be something like what is the equation at node 2? What is the equation around the loop? What is the open circuit voltage? That kind of stuff. If you really understand the material, I don't think it should take you any more than about 40 to 45 minutes. And I didn't update that. You have from 6:05 until I think 6:35 to actually work on it, so it's more than 75 minutes to work on the exam. So you can take all of it that you want. It's really up to you, as much or as little time as you want to take on it. And I'll wait until people are done. And again, it is somewhat shorter than the one that was posted on Blackboard because it does lack the short answer questions, but a couple of the analysis problems might be just 1 degree more difficult, just a little. I mean, like really just a little. More dirty looks. Bring your calculator if you need to. Bring some extra batteries or something. Bring pencils and erasers. I would prefer that you not do the exam in pen. I actually had a student a couple of years ago that insisted on doing all of his exams in red pen. Why? Now I have to switch to a different pen just to grade your assignment. Obviously bring your brain and it's circuits, so smile. Don't bring your textbook. Don't bring any formula sheets. There's really nothing in terms of formulas that you need for this exam. When it comes to later exams, I'll provide you with all of the equations that you could possibly need. Because the class is podcasted, please don't bring any of your iPods or Zooms or anything like that. And leave any wandering eyes at home, because I really just don't want to deal with cheating. This morning there was another big story. For those of you who don't know, I really like pro cycling. There's another story of someone who was taking illegal performance-enhancing drugs to get through the Tour de France. And I do not understand the mentality that drives people to cheat, whether it's in sports or on your homework or your exams. It's beyond me somehow. Last few details, and then I'll open it up to any questions that you have. If you don't have anything, you can go ahead and leave. But the exam is tonight, starting at 6 o'clock. Like I said, I'll try to get there a little early. And it's not in class. I forgot to delete that part. It's in ERC 214, so everything should be opened up and ready to go. For the online students, I have already sent out the password to your proctors, and you'll have until Friday evening at 6 o'clock. If you needed to take it early, I think everybody's talked to me about that. You have like I said, you actually have like an hour and a half or 90 minutes to complete the exam. I'll just be sitting there waiting for you. And if you have any questions, please ask them, either now or when I get back to my office or whatever. If people don't show up, the likelihood is that I will go home and spend a little time with my family in the afternoon and come back. So if you don't have questions soon, I will assume that you don't have questions at all. So if that's not right, please let me know. So are there any questions, any homework problems you want to see me do or anything like that? Yeah. Yeah.
It's the second problem. It says, what is the contribution of the sixth source to the current? I was just wondering if I was doing it correctly.
The answer is that should be solved as a superposition problem. So turn off the other source and solve for the current. Is that what it is that I asked you to solve for? So turn off the other source, whatever it is, solve strictly with the 6-volt source or whatever. Find what the parameter is from that, and that's all you were supposed to do. I think I recall people, about 3/4 of the students understood what I was asking, and they understood that it was supposed to be a superposition problem. But enough didn't that this time around I took that out and put in a dependent source problem instead. Do you want to see it worked out, or? Okay. Any other questions on the Scoop exam, homework, quizzes, anything? All right, we'll see you guys at 6 o'clock tonight then. If you do have questions, my office door is open, and have a good one.